Hello, it's Amanda from Realise Beauty, and I thought what I'd do today is share with you what I'm doing, basically. So I'm in my kitchen. I've been working at home a lot, more than usual, because of the COVID pandemic. I do have my lab down the garden, but often what I like to do is work in the kitchen when there's nobody around, because in the kitchen you can eat and drink, whereas in the lab you can't. So that's why I'm in here. And what I've been doing is trying to create a new method of analysis for your cosmetic products. So what I'm trying to do at the moment is develop a method of testing, a reliable method of testing or evaluating different products that I can employ across the board for lots of different formulas, that's relatively easy to do and gives people meaningful data. So I'm in the research and development stage. This is more my development part, where I'm actually developing a method. One of the things that's happening a lot at the moment is people are wanting to make solid or concentrated products to save on packaging, or so they can access different types of packaging. So instead of plastic, people want to use cardboard, for example, or tins. Now, those two combinations of things, the wanting more concentrated products and the more eco-friendly packaging, have led to quite a few balm type formulas being made. So for example, your solid shampoos and conditioners, your solid deodorants, or deodorant sticks, which have been around for a long time, but they've taken on a new lease. Moisturisers that are more of a stick moisturiser. You've also got solid makeups and lip balms, which we've always had. Along with that, there's also the squeezy type of products. So you might have an Oleogel, which is an oily based jelly that you'd want to pack into a tube. Now that's what's happening in the market, those sort of formulas, which are basically water-free or water-light, so they're more concentrated. And I want to find different ways of testing them so that I can give you some data on how they perform, how likely they are to pass the stability test or to pass the test, and basically how your consumers, your public, is going to experience them. The test that I'm developing right now is to do with the squishing of a balm. So when you have a balm product, it's usually solid or semi-solid, and when you apply force to it, the force will change the shape and the flow of the product. So in a balm, you might put your finger in and it starts to melt because it might have a low melting point. It might sort of push the product out to either side, so you make an indentation, like a bit of a hole, if you like a sand hole, not a sand hole, a snow hole type of thing. It might just glide across the top and slowly sort of, diminish that way. But whatever happens, something's going on, and it's the physics. So you apply pressure to the product and it will yield to that pressure. It will bend and stretch and flow or not. Some of that type of formula, oh, birds having a fight. Some of that type of formula, when you press them or squeeze them or whatever, they'll let out a bit of liquid almost, like they leak. That's one of the things I'm exploring. I want to know how we can predict that. You and me, not people who've got thousands to spend on equipment. How can we predict that? How can we measure that? And how can we then work to prevent that? So that's one thing. Is this a leak-prone formula? The other thing, and why does that happen? So I kind of already know that, but I'm going to hopefully explain that in pictures and methods and testing and that kind of thing. The other thing that I want to explore is yield strength. So not yield strength, sorry, wrong word, compression strength. So how much resistance do different formulas have to pressure? How much can you squish them? And when you squish them, what happens? So that sort of, do they leak, or do they change their form? Do they change their characteristic inside when you apply pressure, or do they stay the same and just deform a little bit? Do they crack? Do they form these fissures through them or not? So I'm looking at what happens basically when you press or squeeze a balm of any type. The first part of this is a big project, but the first thing that I'm, well, it's not really the first thing. And one of the early things that I'm looking at is how a balm, or the balm if you want to talk about one thing, interacts with its packaging. So I made a formula and I'm going with metal containers, this sort of thing. So this is a little one, bigger ones. The formula is not the most important thing in this experiment, but it's something that I can rely upon. I then make a batch of that product so that I can then test it. So my first variable, the formula, I've ironed out because I've got a formula. I've ironed out batch to batch variations because I've made lots of the one formula. Well, not lots, I made 400 grams, which is actually very small, but it's enough for what I'm doing today. So I made my stock batch of this formula, and then what I wanted to test was the reproducibility of my method of squishing. How do I squish these? And I'll talk to you about that in a second. And I also wanted to concentrate on a particular packaging type, and that's the tin. So my question, what I'm trying to establish in this, is whether the size of the tin matters. So if I squish a little tin, do I have to put the same amount of force down to I don't know, complete the experiment, to complete my squish, as I do if it's in a big tin? And that's really my question. So my hypothesis might be, for example, that it takes more force, I have to apply more squishing pressure to make an indentation into a small tin than I do into a large tin. So that could be my hypothesis, something like that. And then I go and test it. You have to test a lot to get reliable data if you want to get statistically valid data. So basically what that means is if I want to know if something is a good method, I've got to do it again and again and again. I can't just do it once. I've got to test multiple samples on many occasions to get a body of data. With this particular test that I'm doing, I will be looking to get around 100 data points per change that I make to my question. The reason scientists do things again and again and again, the same thing again and again and again, and I must stress that we try to do it exactly the same each time. The reason for that is so we can analyse our results and we can make sure that we didn't get a fluke great thing happen or a terrible thing happen that actually won't really happen again. So doing science is that, really. Doing science. Not a good way to put it. So what I'm going to do now is take my samples over to the test equipment, and I'll explain there what I'm going to do with that. I'm not going to test these samples yet because they're still too warm, I can feel them. I really want my samples to get down to room temperature because temperature with Oleogel formulas is extremely important. If I test these at 25 degrees, I'll get a very different result to if I test them at, say, 18 degrees. And again, a very different result if I test them at, say, 5 degrees. So the other thing to note on that is because I'm testing Oleogels, I must use the same method of manufacture. This isn't really manufacturing, it's just little lab batches, but what I'm doing is heating, melting the base, pouring it into the containers and literally leaving them to stand and air dry. That is different to me putting them in the deep freeze and flash freezing them, or putting them in the fridge, or mixing them mixing the batch as it cools. The reason that's important is because each one of those methods creates a different internal structure or arrangement in the Oleogel. That's another experiment we could do. That's something that I've done before and got some data on, including microscopic analysis. So I know that it matters how I prepare my samples, so I'm trying to prepare them the same way. So before I show you my equipment that I'm going to use to do the squishing, what I wanted to do is talk a little bit more, just briefly, about my hypothesis, and that's that I feel I'll have to use more force to squish down, press down on the smaller tin than the bigger tin than I do in the bigger tin. So that's the hypothesis, is something you prove or disprove with data, and I'm going to test these things to get some data that will then allow me to answer my question or my hypothesis. You know, am I right? Am I wrong? You might not have thought of that as something that's important, or why you know, you might be wondering why I'd start there. Well, kind of haven't started there. I'm doing lots of things at the same time, but this is just what I'm working on today, which I thought was interesting. Secondly, it's actually quite common, as you all know if you've got a brand, to put things in the same formula in different sizes. You know, your travel size or your lip size, your body size, whatever. So I don't want to assume that just because these are the same, from the same manufacturer, the same supplier and the same material, that they're going to perform exactly the same no matter what size they are. I want to test that, so that's what I'm doing. If I find that the pressures are the same, then my hypothesis was wrong, the data's still valid. The reason I thought of that as a question is because there is another thing that I'm working on, and that's the overall interplay between the packaging and the balm. So the relationship between them, and the size of the container is all part of that as well. So it's kind of like a multi-layered research project that I'm doing at the moment. Lots and lots and lots of bits, and this is kind of a simple bit and it's got another bit to it. When you apply force to a product, when you squish down, and you might press down, say like, oh, you might sort of poke something like that, or you might squish it like that, or you might rub it like that kind of thing. So they're the kind of forces that we're dealing with here in a balm situation. But when you do that, something happens to the product. The product will be displaced by the force that you apply to it, and it's got to go somewhere. So you press down, the product might come up, it might go out, or it could go down. How far it travels has to be somewhat related to the size of the container, wouldn't you think? And otherwise related to the amount of force that you apply. My machine is making sure I'm applying the same amount of force each time. So that's a variable that I've gotten over almost. I'm still validating that now, but pretty much I've got a good machine, even though it's fairly cheap and it's manual. But I want to know, if I press down here with the same force as I press down there, is the container going to push back to the same degree? Is it going to make a difference? What that matters to the customers who might get these products is if they perform the same, if the same pressure performs the same, then the customers are really not going to have any practical difference what tin size or what pack size they buy. If it takes more pressure to get the product out of a small tin than it does to get out of a harder tin, I could expect it to be harder to apply this product than this. So what seems to be a bit of a bizarre or a kind of, well, who cares type of thing to look into can have quite a lot of implications down the line, not just in terms of is it stable or not, yes or no, or to what degree is it stable, but also to what level is it a practical product. Is it something that people are going to enjoy using? If they scale from the travel size to the big size, are they going to have the same experience with the product, and vice versa? In terms of measuring the force, I've had this little force gauge, which is here. It's a EFG 50 force gauge. I've had this for a while now. They still make them. It's a good little handy device. And what I have used this for before is testing the tensile strength, I think that's how you call it, of hair. You can apply the force in different ways with these different nozzle heads. So I've got a little sort of dot one here, and I've got like a sharp point one there. So if you think about a sharp point one, that's not the same, but that would be the closest thing to kind of pushing your finger into something, I guess, if you like. So just pushing my finger down like that. If you think of this one here, it might be the same as gliding something under your armpit, for example, or across your lips, or pressing it down with your hand, which we don't tend to do with a cosmetic, but you could easily imagine, your skin coming into contact with the product and it's sort of gliding across. What I'm testing is the sort of downward force, if you like. So what I've done is I've got my husband, who's very handy, to make up this little plaque thing on a stand for me with my machine in it, so I can turn this on and then just use this so I can set it all to different levels and whatever. So when I do one full swipe of the handle, it will go down and then up and apply some force. Now the resistance, so that going down like that, all it's got to get through is air. If I put my hand there, it's got to go through my hand, so you've got to put a bit more force in it. If I put a product there, the product's going to eventually break or form a divot, and that's going to record how much force it takes to do that. So I can compare one balm with another balm. This one's harder than that one. Look at this. In some ways, when you're doing that, it doesn't matter what the number is. It doesn't matter what it says. It's really a comparison. So if you've got a product that you like and it's got the right hardness and you've made something and you want to know if yours is going to perform the same, well, you can compare them. I could do tests on one and then test on the other and say, yeah, they're similar, or no, yours is softer or yours is harder, or when I do this to yours, it cracks. That's quite good data for people. More important than me just giving you lots of numbers that perhaps you can't even understand or relate to unless you've done a lot of training on what the numbers mean. So I've set up this machine, and one of the things that I'm doing today, among other things, is repeating an experiment to make sure that the method of measuring I've got is reproducible. So when I'm testing this, essentially the same formula with the same amount in the same size tins, so I've got 10 of these little ones and I've got 4 of these big ones, I want to see if I'm getting good reproducibility of my figures. And then what I also want to do, so mini experiments within one. And what I'm focusing on as my big hypothesis is does it take more force to get a little dent in this than it does to get a dent in that? The one thing you learn about science when you start looking into it is that a question gives birth to a question, gives birth to a question, and before you know it, you're overrun, a bit like having rabbits. So I've finished off my testing, and I've got my holy balms. So I've got my data, and now I've got to process that data. So that involves putting it into my spreadsheets and then performing some statistical analysis on the data to make sure that when I'm doing the pressing or the squishing, that it's giving me a range of numbers that are that make sense. You know, I don't have some extremely high or some extremely low numbers. Now on that, with the method that I've got, it is very crude. It's not ideal. So me manually using the press to press down, the speed that I'm bringing that force down onto the product is still somewhat variable. By using me as the operator and by getting in a rhythm with the pressing, it kind of eliminates some of it. It's definitely better for me to do that than if I had different people coming in and doing a round of testing for me. I might expect a higher level of variability. And that's because the downward forces, the physics of that force, are influenced by the speed that force is applied. So if I was doing this optimally, I would have a robotic arm that came down. That's definitely something that I could do, and that was to be a process improvement that I could look into. You might have noticed that I was poking holes in the products all over the place, not necessarily in the middle, just all over the place. And I have been making notes in my lab diary, believe it or not, that's what that is, about that. So I've been basically making notes about, you know, the first press, the second, the third, the fourth, the fifth hole, the holes, not presses, so that I can see a counter trend, or whether there is a counter trend where maybe the first time I do it in a virgin balm, is it taking more or less pressure than when I do my last one. I absolutely am avoiding the hole I've just made, so I'm trying to always get a piece that's sort of still compressed. But again, that's another bit of data. So the more holes that are already in the balm, the more likelihood there is that the next one I put will be near enough to other holes to be influenced by them. What that means is when I go down with the pressure that I'm pushing down, it might yield more easily, and it does. I've seen it already. If there's a hole next to it on either side, it can slide out the way, as opposed to having to force its way into a new space and then displace more material. R&D takes a lot of time. There's a research phase and a development phase, a lot of testing, a lot of doing, but also a lot of reading and a lot of planning. You have to come up with some good questions, you have to think about your variables, what can you control and what can't you control, and then reproduce your testing a lot of times so that you get a patch of data that has ironed out any crazy things as much as you can, so that you can really get a bit of analysis on that data and make sure that the information you're getting is real information that's valuable. I will catch you again another time to update you on this project, how it's going, and hopefully where you can get your products tested via the method that will come out of all of this work.